Good afternoon, everyone, and welcome to this seminar, ERIIP NERC Showcase. My name is Owen Jenkins of CERIA, and CERIA provides support to NERC, especially in brokerage and dissemination of the NERC ERIIP program. Also, I believe that Katie Hart from NERC is on the line, who many of you will know, and I believe Ruth Hughes from NERC is also joining us later. Next slide. In the broader sense, the NERC Innovation Programme is about partnering with business to help find and use the environmental science they need. And what that really means is understanding industry needs, brokering access to data, making partnerships, translating existing research, and more importantly, applying the outcome and know-how from that existing research, and co-designing research so that industry and the impact as a result of undertaking the work is maximized. So what is ERIIP, the Environmental Risks in Infrastructure Programme? It's an innovation programme. So that is all about using tools and know-how from existing research and applying them to specific industry issues. And the emphasis there is applying to issues that are being undertaken and experienced by the industry and fostering a partnership working between academics and industry. As you can see from the slide, the programme has an extremely wide coverage across a range of environmental hazards. I won't go through them one by one, but it also importantly covers multi-hazards, because many of the challenges arise from when more than one such hazards occur concurrently or in rapid succession. The ERIIP programme members are shown on the slide. The ERIIP programme form a guidance committee, and they help to steer the programme. And they have advised over the past 3 years or so on key themes for the call, the balance of the programme, and as you'd have seen from this year's call, emphasising particular areas that they believe should be looked at. The calls aren't restricted to ERIIP members, however, and as you can see from this slide, which is just a selection of other research partners within the programme. As you can see, they cover transport, energy, water utilities, local authorities, and communications. So it is a very broad-based participative programme. I mentioned at the start that one of CERIA's roles is in promoting and disseminating the outcomes of such work. And as each of the projects are completed, a case study is produced summarising what was learnt over the course of the project. And also we're undertaking a number of themed showcase events, of which this is one. In fact, this is the fourth in the series. The first was on renewable energy. The second one was on the water sector. The third was on geotechnical hazards. And of course, today is on storm and extreme weather events. And I understand that these webinars are being recorded and they are available on the site. So they are available to people beyond those attending today. So before I introduce the first speaker, just a little bit about the programme today. We have 80 people registered. I think about approaching 40 people have registered so far, so I guess people are still coming on board. Amongst the 80 registered, there are 13 clients and asset owners, 30 university representatives, 27 supply chain representatives, and 3 from outside of the UK. So I hope you can hear us all clearly. In terms of questions, you should be able to see on your screen a question box. Please feel free to submit any questions as you go through. The way we'll be handling the questions is after all 3 have been completed, and we'll try to select a number of questions for all 3 of the speakers. So that's all from me. So without any further ado, if we can get the technology to work, I'd like to hand over now to Owen Tarrant from the Environment Agency. And the Environment Agency is one of the ERIIP subscribing organisations. So Owen is going to talk about the position of the Environment Agency.
Hi there, everybody. I'm hoping that you can see my slides and that is coming through okay. Just to introduce myself, my name's Owen Tarrant. I'm a senior specialist at the Environment Agency, where I manage a theme of research to support the Environment Agency's responsibilities for flood and coastal erosion risk asset management. So I look after that theme of research. So Syria have asked me today as a ERIIP industry partner to give a perspective view on our experience with the ERIIP programme to date, reflect back on some of the risks, the environmental risks that extreme weather events actually arise, and those risks that the Environment Agency specifically manage. I'm going to talk a little bit about where our own research in the Environment Agency sits within a spectrum of research, from basic academic research through to operational practice, and how our own research activities interface with the Environmental Risk to Infrastructure Innovation Programme. And then just reflect on one or two projects that I've personally been involved with during the last funding round call, and just really bring out what has been special about those projects and why they've worked well for the Environment Agency. So I'm going to perhaps start off in the obvious area of flooding, and this is a diagram taken from the Cabinet Office's National Risk Assessment, and this diagram really highlights the risk of flooding to the UK, in particular coastal flooding being the second highest risk in the risk register currently, second only to pandemic flu, but also inland flooding, and also the other storm and extreme weather events and the risks that they propose. So the Environment Agency are actually involved in managing risks from a number of those extreme weathers, but of course flooding is often at the forefront of the work that we do. In terms of our management of flood risk, we're currently investing about £2.4 billion during the period of 2015 to 2021 to reduce the risk to people and property in England. But of course we know with the effects of climate change that our investment needs are going to increase over the future. And we're expecting those investment needs to rise by over £100 million per annum over the next 50 years. This is against a baseline of no climate change. Our best estimate is that this will rise to about £850 to £9 million per annum will be needed to be invested to maintain the risks at their present day level during by 2050, and then we expect that to rise further to 900 million to 950 million by the mid-2050s to 2060s. So flood risk isn't going away and will require a higher level of investment as the effects of climate change actually take hold. I feel like I could produce similar images to this slide after every winter, and certainly have done for the last few winters, but the images on this slide are all from the winter of 2015-2016, where the northwest of England experienced significant flooding that affected many people and property. But of course it's not just people and property that is affected, but also the infrastructure that serves those communities. and the effects of the impacts of the disruption to the infrastructure can be felt for many months, if not years, after the flood event. For example, the Tadcaster Bridge on the top left hand of that image, not only the community was severed as that bridge fell down, but also the infrastructure that used that bridge as a key crossing point in terms of gas and electricity was also significantly disrupted. So there's many other knock-on impacts that extreme weather can actually have on infrastructure rather than the direct impacts themselves. Similarly, the image of Kirkstall Road substation, electricity substation in Leeds in the bottom left hand corner there. Again, that substation, when that was temporarily out of action, lost power to over 100,000 people, including the Leeds General Infirmary Hospital. So the impacts of flooding on infrastructure are wide. The impacts are felt well in areas well in excess of where the direct flood impacts are. But of course, it's not just the risks of flooding that the Environment Agency manage, and we often see the situation change from flooding situations to drought situations and vice versa. And perhaps one of the most stark and recent ones that we've experienced was the switch from a quite intensive drought situation in 2010 through to 2012 to one of a flooding situation. And the drought in England during 2010-2012 was in the top 10 of the short droughts in the last 100 years, but it would have been much worse if it had not ended abruptly with the wettest April and July for 250 years. Until the rains came in April, people in parts of England faced the possibility of the most severe drought since the summer of 1976. Then there were both April 2012 and June 2012 were the wettest actually ever recorded, with more than twice the average rainfall. Floods were then widespread through the summer, and we saw some real exceptional events in Cumbria, Northumberland and Aberystwyth, where over 1,000 people were evacuated from homes and caravan parks. Over 4,000 properties in England and Wales suffered fluvial flooding during that summer of 2012. But what were the real factors that made that sudden switch extreme? Well, the drought itself was unusual because below average rainfall in a number of places persisted over 3 consecutive winters, and the drought really developed significantly during the spring of 2011, which was actually the driest on record for the last 100 years. By March 2012, reservoir and groundwater levels were dropping very rapidly, and record low levels were recorded in many places. And it was looking at that point in time that it was a high probability that this was going to be one of the worst droughts on record. That was until the exceptional heavy rain in the spring of 2012 led to the summer aquifer recharge, which rapidly saw a switch from these drought conditions to flooding instead. And actually, for the first time on record, the summer 6-month flows were actually greater than those of the previous winter, which is a condition that we've never experienced before. It's not all about drought and flooding, however, and there's actually many knock-on environmental impacts that are not so clearly obvious associated with extreme weather events. And what brought this home to us perhaps most markedly were actually the winters of 2009-10 and 2010-11, which were both very cold and snowy. And actually, the winter of 2009 and 10 was the coldest since 1979, about 2 degrees colder than the long-term average. And this had, again, impacts on UK infrastructure. During 2009-10, all major airports had to close at some point due to the adverse weather conditions over that winter. many trains were running on reduced timetables, and the Eurostar service was cancelled from during the December period. We experienced major disruption on the road network. But I mean, what did that all mean to the risks that the Environment Agency typically manage? Well, we actually started to see problems with the use of de-icing agents, both from airports and on the road, and this started to become a real concern. For example, airports can use many millions of litres of chemical de-icing fluids in the winter to ensure that the runways and planes themselves are appropriately de-iced. And these chemicals contain glycols, which can rapidly deplete oxygen levels if they actually find their way into watercourses, streams, rivers and lakes, for example. So we worked hard with the airports and the road authorities to ensure that those de-icing agents didn't have those knock-on impacts to the environment. Another issue that took us a little by surprise was actually the disposal of milk. And it suddenly became an issue as milk tankers failed to collect from farms and complete their daily rounds. So again, we were dealing with an issue caused by extreme weather that we hadn't quite foreseen. As a result of this, a review of UK preparedness for snow events was undertaken, and we explored a number of scenarios with government and developed plans which looked at possibilities of rapid snow melt leading to flooding, for example. So that was just a quick overview of some of the examples of extreme weather events and the effects on the environment and the role of the Environment Agency and how we seek to manage those. Just want to turn now to our own research in the Environment Agency and put this diagram up, which presents a flow of research from basic research typically carried out by our academic institutions and our research institutes that flows through applied research, development and piloting, dissemination and training and implementation into practice. And our research in the Environment Agency typically sits firmly in the middle in terms of development and piloting research as it comes through from academia. And we're working very hard with our operational colleagues and end users to actually ensure that the research that we take on board is adequately piloted and trialled in real life operational situations. And working with the likes of Syria, for example, to create supporting dissemination and training material to ensure that research is properly embedded into operational practice. So as this diagram is shown, it's a line, but it could easily be shown as a continuous loop, because whilst we're working with our practitioners, we're trying our best to understand their needs and the research gaps, and we're using that information to then help influence and partner with our academic partners to ensure that the right sort of research is being undertaken to fulfil our needs. So the ERIIP program itself has been extremely useful to us because it has really helped bridge the divide between applied research and that development and piloting, which we need to do and ensure that we do well to ensure that we've got the confidence of the practitioners that this research is proven and can be used in the operational environment. So I just wanted to briefly show just two examples of some work that has come out of the ERIIP program that I have personally been involved with. No means saying that these are the best things out of the ERIIP program, but the ones that I've been closest to and I think are good examples of where academic research has been really well piloted and trialled and demonstrated to be useful within real-life operational environments. So the first one is work led by the BGS, British Geological Society, and their geophysical research team, who've been developing a low-cost, low-power geophysical survey instrument that can actually be deployed in the field and left to record in real time. And the photographs you can see there is of this instrument being installed on one of our flood defences along the Thames estuary. And this instrument has now been fully installed and is successfully returning results back to BGS for interpretation. So this instrument is being left in the field for a year or more to experience the loading over a complete seasonal cycle of that flood defence in the Thames estuary. And it's giving us a real important insight about how that flood defence actually behaves during periods, wet periods, and changes during the tidal cycle. And it's allowing us to develop a more detailed management response for that flood defence. The example on the right-hand side is work that we've been partnered with Southampton University, which has looked at the issue of coastal landfill and how the presence of historic landfill at the coast may or may not be limiting aspirations for shoreline management in those areas. And this piece of work has taken some very detailed developed some very detailed case study material where we've actually looked at real life examples of coastal landfill and developed engineering options for the remediation of that landfill and detailed costs as well. So that is produced a lot of important information, but has also pointed the way and identified the need for some future research in that area as well. So that's been particularly fruitful for us. So I'm going to finish there. It was a quick whistle-stop tour of some of the extreme weather events that the Environment Agency has experienced and has been involved in managing the impacts of. So I hope you've got a bit of a flavour of that, where we sit in that research spectrum and how we can potentially partner with academia to ensure that we're feeding in real-life end-user needs. And just a quick example of two ERIIP programme projects that I've been involved with and why they've been successful. So at that point, Owen, I'm going to stop and hand back to you. Thank you very much.
Thank you very much, Owen. And that was a very helpful presentation, particularly as it's showing the impacts and interdependencies. And when we were setting up this series of NERC showcase events, we were keen, and whilst it's very, very important to publicise the research work that's being done, and we'll hear that from the next two speakers, we also needed to make sure that ERIIP members themselves could share their challenges with the academic community. As many of you know who have also attended the brokerage workshop, and what we're trying to encourage in this programme is pull from the industry on what their needs are. So thanks once again, Owen. I'd like to now hand over to Dr. David Jarosławski from University of Birmingham, who's going to be talking about real-time surface water risk mapping to support local emergency decision-making. Sorry, weather-induced single... Yeah, that's right.
Hi, thanks, Owen. So yes, I'm going to talk about our project, Weather-induced single points of failure methodology for railways. So this was a 6-month feasibility study, and it focused on reducing the impacts of weather events on the rail industries through a better understanding of the likely consequences of asset failure at various network locations. and our main partner for this was Network Rail. So in terms of the project rationale, so weather-related disruption costs Network Rail on average £50 million annually through compensation to train operating companies and freight operating companies, and that's just the cost to them. Obviously, that doesn't take into consideration the wider social and economic costs. And Network Rail have to deal with the twin challenges of both responding to extreme events on a non-event basis, but also planning longer-term adaptation work, so which points in the network to prioritise. And of critical importance to both of these timescales is the concepts of what the Department for Transport's Resilience Review in 2014 terms single points of failure. So these are critical sections of the rail network which have large-scale impacts for society and economy if they're affected. So this was really illustrated with the collapse of the Dawlish seawall in Devon, which cut off large parts of Devon and all of Cornwall from the rail network. Importantly, the impact varies throughout the network, so this is dependent on the network topology and the timetable. So there are particular sections of the rail network which are critical to the functioning of the entire system. And we did some preliminary work which really acted as the genesis of this project, and which I think exemplifies this really well. So this wasn't planned, but I think this really links in with what Owen from the Environment Agency was talking about, the example of June 2012. So this was an example of an intense storm which occurred on the 28th of June, which was categorised as a supercell storm in some places, and passed across the country and caused damage to several pieces of critical transport infrastructure. So the animation that I'm going to show you shows two types of data for a landslip incident at T-Bay on the West Coast Main Line. So firstly, it shows Met Office rainfall radar data to show the passage of the storm across the country. And secondly, it shows Network Rail delay data, which shows all of the individual trains which were delayed and attributed to this event. So this illustrates the landslip on the West Coast Main Line. So if we start the animation, we see the storm pass across the affected area. It causes a landslip, and then we see delays build up either side of the location. So as the event progresses, we see delays spread as delayed trains knock on to following services and train crews become displaced. These are mostly isolated to the West Coast Main Line, but you also start to see propagation into North Wales and across the Pennines. Overall, this event caused 2,500 delay minutes, with the effects continuing into the next day. The second animation shows the impact of a flooding incident at Barnt Green Junction, just south of Birmingham. And I think this really illustrates the impact that can be caused by disruption to network critical locations. So again, we see the disruption propagating out from the incident site. But this time, owing to the critical location of the site and the network, the disruption propagates throughout the country, and we have delays spreading from West Cornwall to Liverpool, Wales, London, and even Edinburgh. So the aim of this project was to develop a new network criticality metric, which would be specifically for use in informing prioritization of actions during extreme events. So in this project, we wanted to expand from this preliminary analysis of weather-related disruption from single case studies to ensemble of events over many years at the same location to identify the typical disruption characteristics following asset failures. So the objectives for this project were firstly to define the key determinants of network criticality from Network Rail's perspective. So really to try and gauge what type of events they find difficult to manage from a route control and operational control perspective. And this fed into the formulation of candidate criticality metrics, which could describe that potential impact and therefore the potential difficulty of dealing with those sites. Thirdly, we demonstrated the metrics on a Network Rail route, and we also aimed to explore the implications for adaptation actions and extreme events management. So the intended impact of the project was really aimed at both near term, so integration with Network Rail's weather action team process for the allocation of resources during extreme events, and also the long term, so integration with Network Rail's weather and climate adaptation process to inform the prioritisation of work to improve resilience. So in terms of the work undertaken, we chose Wessex as our case study area. We started with initial scoping work, so we undertook a widespread information gathering exercise, again to try to understand the priorities that Network Rail would have in dealing with disruptive events. So we interviewed staff with responsibilities for performance, seasonal planning and asset management, among others. We also visited the Wessex Route Control Centre, again because we wanted to try to get a handle on the operational context that this metric would be applied to, so how the sort of day-to-day decisions about responses to extreme events are undertaken. And we held a network criticality workshop which discussed all of these views and started to sort of boil down the terms that would be entered into our network criticality metric. So in terms of data, as with the preliminary studies, we use Network Rail's trust data, which records the location and duration of any delay to a train and attributes this to a given incident. So we were able to isolate all of the delays that originated in certain locations, and we extracted over 5 years of data for this study. In terms of the novel aspects of the approach, this was at a much finer spatial scale than Network Rail are usually used to dealing with. So one of the observations from the initial scoping work was that Network Rail's existing criticality metric is at a very coarse spatial scale. As this is intended for strategic investment purposes such as track renewal, this makes sense. But as but for the purposes of event response, we wanted to go to a much smaller spatial scale, so that resources could be targeted where they would have the greatest benefit. So this project typically looked at a scale of junction to junction or station to station. So we defined a criticality band between 1 and 5 for each location in the route, which was based on the departure of the calculated metric from the route average. So again, this was deemed to be much more useful than the existing metric for route controllers, which is based on the national average. Hence, for some routes, it's actually quite difficult to differentiate the likely consequences of a failure on their operations. The example here concentrates on the Wessex route perspective. So the locations, so basically these are the locations which are likely to cause the most disruption for them, rather than exporting delays to other routes. From this, we can see that there's a major centre of criticality in the Greater London area, and in particular along the commuter line between Waterloo and Woking. We also have a secondary area of high criticality in the centre of the route, and this includes the lines towards Bournemouth and Southampton. Local centres such as Poole and Salisbury are also important, and as you can see, the west section of the route is mostly low to medium criticality owing to its relatively isolated and sparse rail network. However, there's actually a lot of variation evident at a smaller scale. So if we take the area around Greater London, for example, we can see the importance of the Waterloo to Woking line again, but there are also several highly critical links and nodes which can act as disruptive single points of failure, which again can form part of the decision-making process around the allocation of resources during extreme events. So, sorry, I realised I'm running out of time. So just to mention, the intended use for this is with the Network Rail's weather service app, which is a mobile application which distributes various streams of information about weather and risk to maintenance crews in Network Rail's operations. To talk about some of the limitations and areas for further research, one of the strengths and weaknesses of this approach is that it's based on observed data. So one of the benefits is that unlike simulation work or network graph theory assessments of criticality, this is actually based on real consequences. So we can tell where delays spread to if they go over the remit of different control centres, operational areas. Obviously, there's the difficulty with sample size. So again, this is a limiting factor to the assessment where you actually have low sample sizes of observed events. There's still work to be done on distinguishing between different assets. So again, owing to the sample size, we tended to group assets together in this study. But it would be interesting to see the variable impact of different asset failures. Again, there's also the question about which metrics. So there are lots of different competing perspectives, even within Network Rail, on what should be prioritised. Potentially there are different priorities at the national HQ level to the route level. So that's also something which needs to be explored. There are also multimodal considerations. So again, this is only looking at the rail mode. I think there's a case for multimodal criticality. So whether you can still continue your journeys or operations on other modes. And it's also important to look at other modes of transport in terms of access as well. So I think the next presentation may well cover this. But for example, one of the cases in the Wessex route was during the EU referendum day last year, where you had again extreme storms and critical infrastructure were damaged by lightning strikes, but the maintenance crews were not able to access these sites due to concurrent flooding on the road network, and we had 60% of South West trains service were cancelled or significantly delayed in the Wessex route. So finally, obviously we only see this as one layer in the event response and long-term adaptation decision-making process. The ultimate aim is to move from link criticality to asset criticality, where actions can be targeted on specific individual assets. The idea is to link existing quantified knowledge on the relationships between weather and asset failure for different assets, the likely consequence of their failure on link functionality, and the criticality of the link itself, therefore giving a guide to the specific assets that should be targeted during extreme events response operations. Obviously this is a longer term picture and really relies on more accurate intelligence on asset location and condition. So I'll end there, and if anyone has any questions, then I'll be happy to answer those after the presentation. Thank you.
Thank you very much, David. Can I repeat that and sort of say, if you do have questions for either Owen or David or Dapeng, who will be speaking next, please send them in using the question box on your screens, and we'll try and keep a little bit of time at the end of the meeting for questions. So without further ado, if I could ask Dr. Dapeng Yu of Loughborough University to give his presentation, and he is going to be covering surface water flood risk mapping.
Thank you, Owen, for introducing me. And my name is Dapeng. I'm a senior lecturer in geography at Loughborough University. The project I'm going to talk about today was funded by NERC and the ERIIP project. It was a short pilot project started on the 1st of June 2016 and ended just last month. And this project was supported by a number of stakeholders, in fact 8 of them, including central government support from Cabinet Office, DCLG, and local support in Leicester City Council and Leicester Resilience Forum. Environment Agency is also one of the project partners on this project. So as the title of my PowerPoint suggests, that this is a pilot project, and the aim is to pilot a surface water flood navcasting system for emergency responders in cities. And there are 3 key words in the title. First, our focus is on cities. So our work is done in cities. And secondly, the system is intended to be of use by emergency responders in this particular project, although it can be used much widely, as you will be able to see. And thirdly, we are looking at surface water flooding, which arise from heavy rainfall, intense rainfall within a few hours, instead of fluvial flooding rising from river channels. So the terminology flood navcasting is a relatively new concept for flood risk management. And in fact, I think we are not the first one that coined this term, and it related to weather nowcasting. The weather nowcasting as defined by Met Office as a technique for a very short range weather forecasting based on the current weather conditions, based on the speed and direction observed by the radar system, for example. And in the UK, and this refers to 3 to 4 hours for winter rainfalls. And for summer thunderstorms, it's typically less than 2 hours ahead. In this project, we define surface water flood nowcasting as the prediction of flooding from heavy rainfall for the next 6 to 7 hours. So this is based on weather forecasting and nowcasting. So this diagram shows you the overarching framework of the system that we have developed. So there are 3 major components. So the first one is the data server. So we need rainfall data. We need rainfall nowcasting data. And this is provided by Met Office. And the data will be processed in real time and then used by a flood model called flood map. And then eventually the result will be displayed in real time through different platforms. I'm going to go through these three servers one by one. Firstly, the data server. So the animation that you see on the right-hand side is what is available in the USA. So basically, this is the forecast of rainfall for the next 6 hours, and the resolution of that is 5 kilometers by 5 kilometer pixel. If you zoom into a small area, you see 5 by 5 kilometer can resolve the convective storms. Therefore, it will be suited for flood modeling. And this product is also available in the UK, but technically, you can't display it on the web platform. And the Met Office is a project partner to this project. Therefore, the data is made available to us. And the data is similar to what we see on the TV. That is the rainfall forecast for the next 2 days. Apart from that, it is ensemble based, which means there's not just a single prediction. In fact, there are 24 ensemble predictions of rainfall for the next 7 hours. And the pixel size for the UK prediction is 1 kilometer. So we acquire data for cities, and there are different types of products. And because we are focusing on nowcasting, which the product that we use is 7-hour prediction. So this is the rainfall, which is the data aspect. Once the data is received, it will be processed immediately and then used by a flood model called flood map. So I won't go into the details of this slide. And basically, flood map is a flood modeling tool, which I developed over 10 years now. In 2006, first published, and then in 2015, incorporates surface water flood modeling capacity and a few publications. If you're interested, you can look into floodmap.org. That contains all the information. So once data is received, model operate on the rainfall data, give you predictions of surface water flooding. Then it can be mapped to different platforms. Common Office is one of the project partners, and we supply data in real time to them. But there's a standalone system as well. So in the next few slides, I'm going to demonstrate the system using a few animations. First, I'm going to look at, show you the overview of the system, and then we look into the details of forecast for Leicester City. And also we did some work in New York City in relation to Hurricane Sandy in 2012. So the animation I'm going to show you is a standalone system. So there's a login to that. And once you log in, and you will see a picture of the UK. So the red polygons are the locations where we have established live forecast of surface water flooding, and the blue polygons are the cities that we set up already, but due to computational resources available to us, and it's not running at the moment. So these are the cities that has become alive, and there's also a few demonstration versions. And our case study is in Leicester City, and you can click on polygons and zoom into different areas. And overall, there are 14 cities in the UK that we have covered. Some of them are live, running every 3 hours, and some of them are set up and not running, as I said previously. And our case study is in Leicester City. The next few minutes is going to show the animation that we did for Leicester City. So on the top of the screen, you can see the issue time. What we see here is issued on the 5th of September, which is today, 2017, at 10 o'clock. The prediction is into the next 6 hours. So there's a time bar on the top. So what we see here is the different options in the system. On the base layer tab, and we can map, for example, the locations of fire stations, ambulance stations, and nursing homes, and also the data provided by environment agencies, such as the surface water hotspots in the city. We display data into the system, and surface water flood risks defined by environment agency, and this is 1 in 100 years events. This is places that could be flooded if there's a 1 in 100 event in Leicester City. Observation data, and we're working on that, and some needs to be done later. But the project is really about forecasting. So this is about the first tab. And the 2 levels of forecasting: city level, city scale forecasting, and also there's a hotspot level forecasting, which offers much higher resolution forecast. So the color represents the water depth, which is on the top right-hand side. And you can zoom into the system and look at the details. The resolution that we did for Leicester City is 20 by 20 meters, much finer than any other surface water forecasting systems that we know. And the time bar shows there's a prediction every 15 minutes. As we said, the system runs continuously for all the cities, and every 3 hours, and there's a prediction. And you can also overlay, for example, this is traffic data, live traffic data from the Google map, and you can start to look at the interaction between surface water flooding and traffic. By the way, this is a hypothetical flooding, as it's a big event. Therefore, this is not a real picture of what happened in Leicester City. And we also did some work in New York City and looking at Hurricane Sandy. And this work was done together with East China Normal University and Princeton University. And basically, it's coupled storm surge modeling and flood modeling for a lower Manhattan area. Again, the color represents water depth, and the time, this every 15 minutes, there's a prediction of which places could be flooded. And you can zoom into the system. By the way, this is a web-based system which has an API can be called upon. So in this case, the resolution we have done is 3 meters, so quite high resolution, allow you to look at basically a street level predictions of surface water flooding. And the work has been published last year. So the unique point of our system, basically, as you can see, we focus on cities. So we do surface water flood forecasting city for city, and we are not looking at outside areas. And the resolution we offer is unprecedented, can be between 2 to 50 meters. We also did some work in London looking at the referendum day flooding, which is on 23rd of June, and there were 300 incidents attended by fire rescue services on that night. And we believe this is the first real-time flood nowcasting system of its kind in terms of the way that we deliver the results and the way that we model the resolution that we offer. And in fact, we did a BBC East Midland interview in April, and the first sentence they said is that a world-leading technology have been developed, which we happily accepted. And it's also stated that it could be used across the country and around the world. And we hope to get more resources to cover more cities in the UK in the coming months. And thanks to NERC, which give us some additional funding, allow us to do a scoping study for Bangkok, Cosimo, Kampala, and Shanghai, which is ongoing. And this work can also be replicated for fluvial flooding and coastal flooding. So you will ask, yes, you can predict surface water flooding. So how useful can be and who can use that? This is something that we are looking at the moment. So we think city managers, emergency responders, and asset owners, just to name a few, can use this. And for what purpose? The system can be used for strategic planning and also for operational support. And I want to give you a few an example in the next slide. So this is, again, this is the platform. And we look at all these 4 tabs. What we didn't look at is accessibility. So by accessibility, we mean within a certain time frame, how far the emergency responders can travel from a certain station. So there's a 8-minute legislative time target for emergency responders in the UK. And basically, the government requires that they must reach high priority, life-threatening incident within 8 minutes, 75% of the time. And in the last 5 years, and they rarely met this target. And in fact, this is something that become a headache for many of the ambulance trusts in the UK. So the work I'm going to show you in this slide is basically what we did in the last ERIIP project, which is the project before this pilot surface water flow modeling project. So there are 5 ambulance stations in Leicester City. And if we look at the spatial coverage of these ambulance stations and the normal conditions within 8 minutes of their driving, assuming normal traffic, and this blue area is the area that can be covered by these 5 stations, assuming no flooding. And then if we put flooding into the system, the route will be blocked, and these are the areas that will be covered by these 5 stations, because some of the routes will be submerged, and the depth will be much higher than you can safely get past. For example, the blue areas here shows you the flooded areas, and this is a design surface water flood event, 1 in 20 years. And the data set is provided by the Environment Agency. And then if you look at a 1 in 100 years event, and this is the area that can be covered by these 5 stations within 8 minutes of their drive, assuming normal traffic. And if there's an extreme event like a 1 in 1,000 years event, the spatial coverage of the city by emergency responders, in this case ambulance stations, will be much less. So the work has been published in 2 recent papers, and also we are doing a national assessment for England at the moment, and make some good progress. And we are also working alongside New York City and Shanghai, and to do similar analysis for them. So this is a pilot project, and there are many remaining challenges for future investigation, but also we think there are a lot of opportunities for us. And the key challenges that we see, as you will ask, I guess, is how do we constrain the uncertainties in the system. So for example, rainfall forecast, and there are ensembles of rainfall, 24 of them, and which one do we use? And this is something that we really need to understand and to do more investigation. And also how do you represent the urban microtopography, and all the cities you need to calibrate and validate your forecast. We did this for Leicester City, and we didn't do this for other cities due to time constraint. And most importantly, how do you communicate this uncertainty to different stakeholders? So I will stop here, and thank you very much for listening. Welcome any feedback.
Thank you, Zapeng, for another very interesting presentation, and just shows with the sort of challenges faced within cities, particularly in terms of looking at vulnerable people and emergency services. No questions have come in yet, so this, I guess, is your last chance if you do have any questions for Owen, David, or Dapeng. There's a couple of minutes of broadcast time left. While you're thinking of any questions or typing any questions in, I'd like to take this opportunity to thank Owen, David, and Dapeng for their very interesting presentations and for preparing for this and for giving the presentations today. I'd like to thank you all for joining and listening in. I hope you found it valuable and of interest. After the event, we will be sending a feedback form over the next few days. We will be making the presentations available, and in fact, a recording of this webinar will be available. Within the feedback forms, we'll be asking those of you who require CPD for professional institutions and so on, this will account for 1 hour's CPD, so if you require that, please let us know. And in the meantime, we have one question, which I'll read out. We have a few questions now. We'll start with the first one, till time runs out. How accurate was the forecast flood model for Hurricane Sandy versus the actual flooding there? That question from Sarah Lupton. So one, I guess, for you, Dapeng.
Yeah, the prediction of for Hurricane Sandy is very good, in fact, and I didn't show the outline of the recorded flood extent. On the east side of Lower Manhattan, and it's spot on. On the west side of Manhattan, and there's some differences between prediction and observation. But bear in mind that the observation is really is not accurate observation. Observation is an outline that derived from point data by the US government, and basically is a GIS-based overlay of the landscape with the point height. Therefore, you will have overestimation of observation.
Thank you. And there were a couple of questions relating, targeted at David, and asking the role of Network Rail and the extent to which you were able to work with Network Rail during your project.
Thank you. Yeah, Network Rail were extensively involved. So really, the first few months of the project were really based around an intensive knowledge gathering exercise, really to try to understand their operational context. So how they make decisions about extreme events, what the process is in terms of the extreme weather action teams, where this metric could fit into that decision-making process, and really in the sort of definition of what is a disruptive event for them, which went into the metric itself. And I'd also like to thank Network Rail for the access to data as well. So we used about 5 years of over 5 years of rail delay data, which Network Rail supplied, and also it was very useful having access to the route control center as well. So we were actually able to enter into the operational environments that Network Rail operate in, and actually got feedback on how our metric could be used in that context.
I can interrupt you there. I think after this webinar, we can make the connection between yourselves and David Butcher at Network Rail to sort of share the contacts of who were involved. One more question come in, so I'm afraid we can't take any more questions now, but I will have one question for Owen, so you've had one question each. Do you think that the UK needs more investment on area of the UK needs the most, west, east or south? A simple question for you, Owen.
Sorry, you broke up a little bit halfway through that. Would you mind just quickly repeating, Owen?
Do you need that UK needs more investment on coastal defence structures? Which area of the UK needs it most, west, east or south?
I'm not sure I can actually answer that question. I think that there's different needs in different parts of the country. We know the East Coast is particularly vulnerable to coastal storm surge, for example. The West Coast has its own issues of often difficult communities, extreme waves, rapid responding catchments. So each of the regions of the UK actually present their own challenges in terms of the flood risks. So yeah,
I should have said that. Question was raised with Dr. Mohammed Haidar at Rationale University. So no more questions have come in. So again, thank you all. Thanks to the speakers. Thanks to those who've asked questions. Thanks to those for sitting in. Keep you informed about future events in this series. Thank you very much indeed. We'll now be signing off.